Okay, Trig, here we are, Q4, week 6, talking about eccentricity. Eccentricity is a measure that we are going to talk about with ellipses. So it's for ellipses. Not for parabolas or anything like that. So eccentricity basically tells you how close or not close to a circle an ellipse is. So we have a formula for calculating the eccentricity. We call eccentricity E, and we use a little italicized E. Don't confuse this with E, the natural base, used in exponentials and logarithms. You should be able to use your context clues and figure out which one is being talked about, but it looks the same, but this E means eccentricity for us. Sometimes you'll see E meaning the natural base. Just use your context clues and it should be obvious. So eccentricity is defined as the ratio of C to A. So we don't always have C given to us. C is the square root of A squared minus B squared divided by A. That is how we calculate eccentricity. And in this formula where A is the semi-major axis, B is the semi-minor axis, and C stands for the distance from the center of the ellipse to either focus. So those letters are what we've already defined them as last week. Same thing. So if we do the ratio of the distance from the center of the ellipse to either focus to A, that will tell us eccentricity. And if we think about it, the distance from the center of the ellipse to either focus, our numerator, is going to be smaller than the semi-major axis A, unless it's a perfect circle. If it's a perfect circle, then they should be equal to each other. So our ratio, C to A, is always going to be between, our eccentricity is going to be greater than 0 and less than 1. It could be equal to 0. That would be a perfect circle. We don't really deal with ones being equal to 1. That would be just like a perfectly flat line. So the word eccentricity actually comes from the adjective eccentric, which means off-center. And if you think about how an ellipse compares to or is different from a circle, it makes sense. An ellipse is kind of like off balance. It's got 2 centers instead of 1, so it's not on center like a circle is. One really cool use for ellipses and eccentricity comes to us from astronomy. So in astronomy, I used to teach earth science years ago, so I've taught astronomy. We have something called Kepler's first law of planetary motion. Kepler actually has 3 laws. The first one is the one that mostly applies to what we're talking about today. His first law says that the path of a planet's orbit is an ellipse with the sun at one of the foci. Now, he doesn't talk about what's at the other foci. Usually it's just an empty point in space. But first law of planetary motion dives in with all planets orbit the sun in an ellipse. And asteroids, comets, other things like that will also follow elliptical paths around the sun. Things like comets and asteroids that go really far out of the solar system will have a really highly eccentric orbit. So their orbit is going to be very stretched out. The higher the value for the number of eccentricity, the further away from a circle it is. The lower the number, the closer to a circle it is. So asteroids, comets have highly eccentric orbits. So let's look at an example. We're just going to analyze Earth's orbit in terms of eccentricity and see what we can discover. How eccentric is our orbit for our home planet? So Earth's orbit has a semi-major axis of approximately 149.598 gigameters. We're going with gigameters because they're way easier to deal with than kilometers, because this is a really large distance. And it has an eccentricity of approximately 0.0167. So this is a very small decimal. What that tells us is that actually the Earth's orbit is really close to a circle. It's just a little tiny bit off. So what we're going to do for this example is we're going to calculate and interpret the values for B and C. So now A, B, and C are related. We've seen it in our Pythagorean relation. So we know that E is equal to C over A, which tells us if I just rearrange this and solve for C, C is equal to E times A. Multiply both sides by A to get rid of the fraction. I've got C is equal to E times A. And I did that because I know A and I know E. So I can plug those in and solve for C pretty easily. So I can say C is equal to 0.0167 times 149.598. And you notice eccentricity doesn't have units on it. That it just doesn't. We just refer to it as the eccentricity. So if I multiply these two numbers, I'm going to end up with C equals 2.4982866. When we're dealing with things in astronomy, we often go out to extreme decimal places because these are super large distances. So a gigameter is going to be something that we might actually want to change into meters. And if I don't have enough accuracy in my decimal points, it's going to be hard to change into meters. In this example, we're not changing it to meters yet. but just something to think about. That's why there's so many decimal places. Alright, so now that we have C, I know that I can use my Pythagorean relation, and I can pretty easily solve for B. I know that, slide this direction, B is going to be equal to the square root of a squared minus c squared. I just got this by rearranging and solving for b from our Pythagorean relation. So I now know a and c, so I can plug them in. B is equal to the square root of 149.598 squared minus 2.4982866 squared. So this tells me that b is approximately 149.577. So I've got b is 149.577. A is approximately 149.598. C is approximately 2.498 gigameters. So here's where it helps to remember where A, B, and C lie in space with relationship to an ellipse. So here is an ellipse. It's got foci. It's got a center. It's got endpoints, vertices, co-vertices, and then I can kind of sketch it in. It's always 90 degrees at the vertices and co-vertices, and then scoops around. So if I think about this, we know that A is the length of the semi-major axis. So this would be A. Half of the major axis, which is halfway across the longest way. We know that B is the semi-minor axis, so this would be B. We know that C is the distance from one focus to the center. That is also this distance right here. The one we most often use is the distance from one focus to the center. So C can be found in two different places, which is true of every ellipse. So if we start thinking about what each of these things mean, then we can start interpreting some of these things. So if I look at the semi-major axis and the semi-minor axis, A is the semi-major axis. It's 149.598. The semi-minor axis is very, very incrementally smaller than the semi-major axis. These two numbers are so close to each other. And yes, we're dealing with large scale things in the solar system, but in the solar system scale even, these are so close to each other that the percent difference between the two, the semi-minor axis is only 0.014% shorter than the semi-major axis. So then we have two astronomy words we should talk about: perihelion and aphelion. So perihelion is the closest point to the sun. In the Earth's orbit, which means that the farthest point is the aphelion. So I can calculate the perihelion and aphelion distance of the Earth from the sun. So let's say that we put the sun right here at this focus. Here's the sun. So we can see that the distance to the closest point in the orbit is going to be A minus C. If I do A minus C, I get that the perihelion distance is 147.100 gigameters. If I calculate the aphelion distance, you see, looking at the sun, I'm going to go C plus A. So C plus A tells me the aphelion distance is 152.096 gigameters. So these are very close to each other. We can see that the eccentricity of the Earth is not actually very far off center. It's very nearly a perfect circle. But the distance between the center of the sun and one focus and the center of the Earth's orbit is 2.498 gigameters. But it's actually not that big. When we start looking at things like asteroids, their eccentricity is huge compared to this. Okay, let's look at some other uses of ellipses. So I'm going to slide over, find some more space. Okay, so next thing to talk about is the reflective property of an ellipse. So, because of their shape, ellipses are often used to make reflectors of things like sound, light, and anything else that kind of travels in a wave. So, let's look at a diagram and see what happens. Okay, so here we have an ellipse, and if I take something and start out at F1, focus 1, if I shoot, let's say, a beam of light at the boundary of the ellipse, what's going to happen is it's going to come over here, hit the boundary. We're assuming it's made of something that's reflective. It's like a mirror. If it's light, mirror would be a really good thing to use. And it's going to bounce off that boundary, and it has to hit back at focus number 2. So what happens is we can figure out exactly where focus number 2 is if we don't know where it is, because we've got this line that you can see here, T. Line T is a tangent line to the outside of the ellipse, so it intersects in one point. And what happens is the angle that the initial beam of light forms with the tangent line is going to be equal to the angle formed with the other side heading towards the second focus. So this is just a function of how ellipses are formed and the function of their shape. This will always happen if you shoot a beam of light from focus 1. It will bounce off the boundary of the ellipse and land at focus 2. So if you think about like taking an ellipse and spinning it along an axis, usually we rotate it in 3 dimensions around the focal axis. It's not going to work the same if you try and rotate it around the minor axis. So if we take this and we spin it in 3 dimensions around the focal axis, remember focal axis is the one where the 2 foci are, you get what's called an ellipsoid. So the ellipsoid is just a three-dimensional shape. So we can make like domes and buildings and stuff in the shape of an ellipsoid. You may have heard of things called whispering galleries in certain like Capitol buildings. You can stand in one focus, whisper, and your voice will bounce off the ceiling and be audible to somebody standing at the other focus. This is another thing that they like to do in like museums, like science museums. Sometimes they'll make a little demonstration of this. So, this is used in healthcare sometimes. So they have this thing called a lithotripter. And what it does is it emits underwater ultra-high frequency shock waves from one focus, and they place a person in the water who has a kidney stone at the other focus. And the shock waves actually are really good at breaking down kidney stones. So let's look at a diagram of what a lithotripter in use would look like. So we've got an ultrasound emitter over here on the left, and it is projecting ultrasound waves right there at that left foci. And then we've got a patient's kidney stone on the right. So it doesn't matter where the ultrasound waves go, they will all end up bouncing off the walls of this ellipsoid and smashing into the kidney stone at the focus on the other end. So let's do an example trying to focus a lithotripter. So the ellipse used to generate the ellipsoid of a lithotripter has a major axis of 12 feet and a minor axis of 5 feet. How far from the center are the foci? So the distance from the center to the foci we know is c. So from the given information we know that A, let's call A, remember that's our semi-major. So A is going to be, our major axis is 12 feet. A is going to be 12 divided by 2, or 6 feet. And our semi-minor is B. So that's going to be half of the minor axis because semi means half. So 5 divided by 2 is 2.5 feet. And then we can use our Pythagorean relation to calculate the length of C, which is the distance from the center to the foci. So C